Okay, so fun things to talk about. All right, so we're going to talk about, we've started with this whole power law size distribution business, which is tricky. It's tricky. People get confused about this. They really do. Even when you know a lot about it, you still have to think about it, as we've kind of observed with probability. So let me actually, it's going to come up. Okay. Let me go back. We actually had, okay, so I forgot about this. Yeah, all right. So we had this example, right? And I asked you to write down your estimates of the quintiles for wealth in the US. Right, so this is from this particular paper by Norton Arrowley, 2011. So actual was up at 85%. This is what people had estimated, which is far more egalitarian. And this is their ideal, which is insane. Okay, so which you're welcome to, you're welcome to set, of course. So and there was some breakdown by demographics. So this is, I know what the problem is. It's not in here. Let me just crush this one. Maybe it's not there. Hold on. Doop, 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 doop. Huh. All right, well, I'll have to find it again. I thought I put it in there. Why would that work? Okay, all right. I'll show you on Thursday what you guys did. Anyway, it's not there. All right, sorry. Oh, I could find it. All right, it's okay, I'll leave it. Okay, so, all right, so power law size distribution. So we got to this, so this is their story. When it wants to come up. Okay. All right, so we're dealing with beasts of this form in here. Right, x to the minus gamma. There's some constant proportionality. There's some range over which this is true. We did this little calculation, complementary cumulative distribution, sometimes called by other names, but we'll call it the CCDF. And we have this very simple little result, it's just a little integral, that we get x to the minus gamma plus 1 for the complementary cumulative. So this is an integration, so it smooths the data out. It's easier to measure this exponent here, and we do it in log-log space. That was the main story there. So there's just a little bit left in this set of slides that I want to connect to. I'll connect these size frequency distributions to what's known as Zipf's law, which has been around for a long time, since the late 1940s. And I'll tell you about Zipf, a little bit about Zipf, what I know about Zipf. He actually, okay, so he passed away in 1950, I think, and he had this great book up here in 1949. All right. So there's not so much known about him that I'm aware of. Okay, so it's a nice thing. It works even when we have a tail, because you can simply just do the integral from when the tail starts, increases the exponent by 1, and we clean up the data. So we'll use this in a problem set. So here's the raw distribution. Again, this is for this brown corpus. So size here is size is the fraction of words that are a particular word. So the, for example, what was it, 6% or 7% of the corpus was the, and then of and and. So they have big sizes, right? So size for words means how many times they appear. Size for elephants is how big that elephant is, right? Okay, so these guys are the elephants, and then we have shrews back here, and these are ones that appear once. And there are many of them. So there are many little things that appear once. They're rare, but as a whole, they make an interesting thing. So if you put all the rare things together, they're dissimilar, but they add up. So if we do the straight integral, right, so for every point, we're going to replace it by how many words beyond it have at least that fraction, appear at least that fraction of times in the text, have at least that size. We get a nice integral. And this, you can see it's not perfect, but you'd rather put a straight line through this thing, cavalier fashion as we do, lots of arguments, than this one, because nasty. Okay. All right. So you can do the same. We mentioned this, so I'm just connecting to where we were. You can do the same if you have a discrete variable. That's fine. It's, of course, now it's a sum. We always do these horrible things, and it's not in here. Where we replace that by an integral anyway, so we're back to the same story. Okay, fine. So we get that same thing, minus gamma plus 1. Okay, so Zipf, right. So Zipf you can actually get it. There's a, well, here it is. You can get this book now. Again, it was out of print for a long, long time, and was selling for $1,000 or something, you know, because it had become a rare book. But you can get it for about $20 now. So human behavior and the principle of least effort, right? So this is the Homer Simpson principle, essentially, right? And you'll see people still working with this kind of same thesis that people are, well, you could either say lazy or smart, all right? Both of those things together means that they will do things. They'll figure out how to minimize their you know, obviously we don't do this perfectly, but figure out how to mete out their energy. That's kind of the idea, given they have some task. So he was a linguist, particularly I think Chinese. Was his specialty, but he was at Harvard, and he started to look. And he looked at. He also looked, as I recall, how children's vocabulary grows with age, right? So how that expands. And I'll show you how he did something. Right, this is 1940s, 1930s. He has a book called The Psychobiology of Language. I mean, so pretty cool words, but. Obviously, he didn't use computers, so we'll see an example of how he did all of this later on. But so word frequency, of course, but was kind of his thing, where he started from, because he was a linguist. But he also looked at city sizes, and we'll see a whole bunch of other examples, because he realized these patterns were out there everywhere in social phenomena. And he had a theory. We'll talk about it briefly. But it wasn't really a mechanistic one exactly, okay? So it doesn't quite say, you know, here's the exponent because of these things. And we'll get into that later on. So Zipf had a different way of approaching, you know, you've got this big collection of things, cities, words, whatever it is. So you've got Moby Dick in front of you. You've tried to read it, and now you're just going to pull it apart and just give it up, right? So now we're down to looking at its words. Anathema, of course, but very interesting, right? There's a lot of interesting work associated with function words. I was just reading about this now again. James Pennebaker, who's at University of Texas, I think that's right, has done a lot with looking at how people use just basic function words, so the and of and these sorts of things, but also pronouns, which we use all the time, right? And they're kind of invisible. But it turns out people in positions of, so if you have two people talking, the one who's in power, who's got the stronger power differential, uses I much less. You can see it in emails, you can see it in the way people talk, you can see it in public presentations, whereas the person who's in the lower position will use I. And it's because we use those words, they're not the rare words, these are incredibly common words. The signature is very strong. So easy things to, you know, overlook and discount, because those words, they're little glue words, they're invisible. I'm not sure about like. I mean, there are these words we just flood our language with, but it's not even the ums and the likes and those sorts of things. It's pronouns. Okay, so Zipf's approach. So language, extremely interesting, unbelievably interesting. Okay, so we have some entities. Let's just rank them by size. So this is a very easy thing to do. We're just going to rank them. So we take the biggest city. That's number 1. So it's going to rank 1, and we'll put its size on the y-axis. Number 2. Is the next city, right? Whatever it is, LA, Houston, you know, if you take the agglomeration, for example. And then you just rank them and list them. So the smallest guy will be right out here, and the biggest one will be at the start. Okay, so we'll say X is the size of the ranked entity. So we have the largest one. So as I said, frequency of the most common word in a text. So the would be number 1, rank number 1, and it would be simply its frequency, or its counts. And so Zipf made this observation that over and over in different areas, so again, city sizes was one of them, language is another one. Turns out, of course, this is somewhat, it's not perfect, and we have very interesting work coming out of our group even that's addressing what's happened in the last 15 years with this. But I'll tell you the sort of the big story. So again, power law decay, right? So it decays, it doesn't decay exponentially or anything, it really does have a heavy tail. Okay. So even if it's not a perfect parallel, it's certainly a heavy tail. Now let's connect these two things. So this is the one I've just shown you, the CCDF. So this is this integrated version of the size frequency distribution. And this is what the Zipf plot looks like. So this is the rank, I guess I've called it I, the rank of the word. And these are the frequencies. So the is here of, maybe it's and, and so on. 6 words comprise 20% of most written English texts, just 6 words. And about 150 words will get you a half of all of the written text. So it's not much. So very hierarchical kind of structure. Okay, so these things immediately look somewhat similar. This is exciting. This is truly exciting, right? This was not actually really noticed, though, until about 2000. So this is lying around for 50 years, people talking about, because the physicists like the size frequency distribution, and this Zipf's law was coming from a different realm. I mean, people understood this, and some certainly understood this, but it wasn't widely known. So there's a paper, for example, on the World Wide Web structure in about 2000, maybe it's 1999. It's this advent of, which we'll get to later on, the whole network story by Flutas, and Flutas, the 3 brothers, and they treat these things as distinct pieces, right? Which is fine, but that's just sort of a good example of how it wasn't connected properly. So you can see that these things should be somehow the same. So let's just connect them. Size is word frequency. All right. So these things are related. So if we flip this one, so if simply just flipped it this way, then you can see they're the same kind of thing. But now we have rank here. This is this complementary cumulative. So this is the number of words that are greater than a certain, in this case, frequency. And this is the frequency across here. This is the frequency of the ith word. Right? So now the is over here, which matches here. The is the biggest guy. There's one word that has its size, right? There's one of that elephant. Not quite right, because there are more than one elephant. All right, so these things are simple, so we'll just make a little connection between them, and we can connect their scaling exponents. Very simple kind of thing to do, very natural thing to do, appears in all sorts of realms. So let's see. So if we take this is our complementary cumulative distribution, this exciting thing. If we take the, multiply by the total number of words, then we have roughly the number of objects with size at least x. Right? So if we go down to the smallest size, this guy has to be 1. Right? At the smallest size, it's 1. If you go to put x at the smallest, the size of the smallest element in the whole thing, then the probability that any random element you pick out is at least that size is 1. Right? That's the way this thing works. And multiplying by n will give you the total number. So n, all of them are bigger than that. So we've gone from probability to frequency, which is just to help us connect to Zipf. So we're starting with the CCDF. And then we just make this observation. So if we have some size, x, whatever it is, then this number is, in fact, its rank. That's actually a comma, not a prime. This number is its rank, right? So these are the number of words that are at least this thing's size. So if you count back from them, 1, 2, 3, 4, 5, 6, up to where you are, that's where you are ranked, right? You can think of the rank. The rank is now traveling back in this direction. So we can connect those two pieces. So as soon as we do that, this is Zipf's law to start with. So Zipf's law is that the size of the ranked object is decaying as out of the minus alpha, so an observation. So we're going to stick the rank, we're going to replace it by this CCDF beast. And as soon as we do that, we can replace this, and it's just a constant of the whole system. We can replace this by x to the hour, it's minus gamma minus 1, right? That was the minus gamma plus 1, sorry. That's how this piece decays, right? So the CCDF itself decays as x, the size, the minus gamma plus 1. Right, and we had a minus alpha here, so those blobs are multiplying each other. And therefore we have, so this, we started with xr, a bit of a funny argument. We started with the size, write all these things through, it has to be proportional to itself. So this blob in here has to be 1. So 1 equals this, and then we can rearrange it. Right, so 1 equals all of this. We could put the, we'll put all of this on the other side. So we've got 1 divided by, and we'll put in some negatives, so we get alpha equals 1 over gamma minus 1. Fine. So that's a simple connection. It's easy to produce the Zipf's law, right? You just, if someone gives you a whole bunch of things and they all have sizes, you just sort them by size, descending, and just plot it. That's it. It's very easy to do. And in fact, you see here that it's exactly the same. So we've talked about some interesting values of, I know they're fascinating to you, exponents gamma equals 2. Right, that was on the cusp of having an infinite mean, which is very strange. Infinite mean, we'll see one of these, we'll see it very, you know, it doesn't seem like, we'll see an example of where you can get an infinite mean, and it just doesn't feel like you should be able to do that, but it's there, okay? We'll go through a calculation that does it. So this is, gamma equals 2 is on the cusp of an infinite mean, but certainly has an infinite variance, where infinite means, you know, it's governed by the size of the system. So very large variance, right at the edge of a very large mean. So that corresponds to alpha equals 1, and this is sort of, alpha equals 1, that's Zipf's story, that this exponent is 1 universally. It's not really true. And it's often just a little bit down from that, and then there are breaks in scaling. We can get to that later on. But that's just to connect two very important values. Right? So gamma equals 3 is another useful one here. Right? So that's the edge where variance starts to become relatively small. So alpha equals 1/2. So what's happening as your size frequency distribution is going down like this, it's losing its fat tail. It's not as dangerous, right, on the log-log scale. Then the Zipf one is actually going up. It's inflating. Zipf is right, it has an opposite tendency. It's an inverse. Just so that is the feel of how that works. Okay, good. And you can see it all explodes when gamma equals 1, right? And so gamma equals 1 is the limit of what we can do with a size frequency distribution. All right, so a simple little connection between those two. Good. Oh, yeah, extreme deviations in cricket. So, had the cricket scores up before. So just to show you, so we've talked about statistics of surprise, right? So here are batting averages. This makes no sense to you, I realize. But in cricket, you can have this average of, you know, if you're one of the world's best ever, then you'll be above 50. It means you make 50 runs every time you go to bat on average. So you can see this is everyone. These are the, you know, the bunnies. These are the, like, right, sort of like, it's a very different game, but pitchers typically can't bat, right? These are people, you know, who go out with like a pitchfork or something. Like they're holding a rubber tube and they're trying to bat, basically. But they're the fast bowlers, usually. Can't bat. Anyway, so there's big distribution. You've got these people in here, make over 60, then you're an absolute genius. There are only 3 in here. But there's 1 point over here. So that, you know, if you think about all this, sports data is incredibly interesting, very rich. Lots of people play over and over. You have progressions. You have all sorts of interesting things. But there's this fellow here. So, and it's this guy, Don Bradman, who grew up in the bush in Australia. And his average was, so if you make 100, you get to wave your bat, and everyone cheers, because it's a big deal, because of the whole 10 digits thing. But 50 matters, hundreds, that's recorded. And he famously had to make 4 runs in his last innings and goes out and gets a duck, which is 0. So they cheered him on, cheered him off. And he ended up with 99.94 for an average. Anyway, this is around this, before and after the Second World War. This is but it's very unusual. I'm just putting this here because this is a very unusual thing. We have a whole body of work now in sports, which is starting up. We're looking at the narratives of games, actually, the stories of games, you know, how well they compare, which kinds of games, like professional sports, have different kinds of stories associated with them, and how variable can they be? What's the taxonomy of stories coming out of games, for example? Right? So this is unusual. I mean, you've got Michael Jordan and you know, it's a game called hockey, right? What's that one? Yeah. You know, you've got your best players, the most famous players in all of them, and they're off a little bit. They'll be up the top, but this is very strange. Anyway, so we're going to get to success later on, and we'll think about, you know, the Mona Lisa and Harry Potter and all these sorts of things, why they're successful. So there's sort of a story for why this guy's successful. There's actually, I'll play the narrative. It's pretty funny.
And this is the first wicket he ever defended, a big iron tank. Here as a kid, he used to bounce a ball and then try to hit it on its return with a single cricket stump. You can imagine how that ball bounced from the round surface of the tank as full of angles as Euclid's pet hedgehog. Bradman never knew which way that ball was going to twist and dart next, and trying to follow its flight gave him an eye like a gimlet and wrists like quicksilver.
Hilarious. So this is very famous in Australia, but I mean, the English, if they got him out, they put it on the front of the newspaper. He's out, you know, like, thank God. Anyway, long time ago. It's a good story. But this is he grew up doing this, and I guess he was that is his story, at least, of why he was had such a good eye. All right, so that's just for fun. I know you're thrilled by that. It is the second biggest team sport in the world, I think. There's a thing with the little round ball, but where they all fall over. Yeah, very different American football, right? It's just completely opposite. You know, if you fall over, you better be basically, you know, your spleen is ruptured or something. Yeah, which happens. Yeah. Or cycling, you know, where basically you have to be cut off on a stretcher. I want to get back. Very different. All right, so I'm going to give you. This is actually, this book I had for a long time, and it wasn't in. It hadn't been reprinted. So I, got myself to a photocopier and pulled out a few of the pages from it. It's an old one. It's a 1960s version, I think. So I'll tell you a little bit about this because it does, connect into where, or at least the social sciences are going. But it's all about many different stories in many different realms. I mean, obviously cities are very different to, Moby Dick. So it was this, what we're trying to go for in this course, which is the stories that go across many different fields. Okay, so he was a linguist, and he got excited about statistical analyses and human behavior as well. So this is his great book, and I mentioned it. So glottometrics, so study of word metrics. There's also glossolalia, which is speaking in tongues. These are just good words. Okay, so this is from the preface, so nearly 25 years ago. So this is 1920s. Occurred to me that we might gain considerable insight in the mainsprings of human behavior if we viewed it purely as a natural phenomenon like everything else in the universe. So this is a bit strong, obviously, but so the purpose of the book is to establish the principle of least F as a primary principle that governs our entire individual and collective behavior. Now, people are still using this, as I said, as a kind of a thesis or a hypothesis for explaining how people behave in all sorts of areas, and because we have so much more data about how people move around and how they communicate, we can test these things out. But that was his idea. It doesn't, as I said, he doesn't have a mathematical, mechanistic story, which we'll see arises in the next decade, actually, in the 50s. And we'll see a bit of a battle between people with very large brains, and one has a Nobel Prize, the other one doesn't, about how it should work. All right. But he did a lot of very interesting gathering of data and looking at it. So, and here's this idea, right? So the principle of least effort. So in solving some problem, something you have to do now against everything else you've got to do in the future, you can think of it like running a marathon. You can kind of mark it out, or getting through the day, through lectures where you want to go to sleep. He will strive to minimize the, obviously this is the 40s, to minimize the total work that he must expend in solving both his immediate problems and his probable future problems. So trying to, not keep things under control, I suppose. So there's this funny thing, probable average of his work expenditure. So this is actually, there's work expenditure, so that could be, joules per second. That's actually put down in that way, right? But he doesn't quite get to that. He did look at these things, and I'll show you a few of these plots. He has, he just sort of has a verbal argument for how this might work. And we'll see that it's not unreasonable. So city sizes, he looked at things like this. Number of retail stores in cities as a function of size. Number of services, barbershops, dry cleaning, that sort of thing. Number of people in particular occupations or in corporations or organizations. Number of trips taken by cars between cities, okay, that sort of thing. By date line, so this is new items, so this is the number of items in newspapers as a function of also, right, so it's also about how far away the location that you're writing about is as well. How much stuff has been moved around the US, telephone calls, people moving around, marriage as a function of distance that the people grew up in, apart. So this the Zipf law distributions that we talk about, but there's also a kind of, and again, there are papers that have appeared in Nature and Science in the last 10, 15 years doing all of this, and we can get to it. I'm just going to try and give you what he had. This is for some of these, it works like this. So you've got two cities, A and B. The amount of stuff that's being moved between them, so this will be proportional to this, is the claim. And so this is a gravity law in 2 dimensions. So population of A, population of B, distance of A divided by the distance between them. So, right, we've got the US. So you're thinking about on a 2D situation. So it's like mass 1, mass 2 divided by the distance between them. And gravity in general, right, the gravitational force is proportional to over r squared, right? That's a 3D thing because you've got a surface and the surface area grows like us. You can think of it like that. But we've got in 1D, we've just got a little opening up, right? Just a circle. Okay, so I'll show you a few plots. So the first story is this claim that frequency of words decreases as rank to the -1. So he explicitly says it, right? That his exponent, which I've called alpha, is -1. So you can play with that and say, all right, well, we can multiply frequency and rank together, and that'll be a constant. Right? So that's one way to present it. So here's the rank of a word. He went through James Joyce's Ulysses. We always go for the hard books to read. Frequency times rank, and you can see these things are pretty stable, right? So it's 1,000th word, which he doesn't show what it is, multiplied by its frequency. So, it's not bad. It starts to, what is this? It starts to fall away towards the end, maybe, and which makes sense. It's got to be a little jumbled. So that's, there's a little start. Here he has Ulysses. There's this kind of ideal one, which he just says is ideal. There's another data set in there. But, if you're looking at this is not bad. It's close to -1. And you start thinking there must be some deep magical story here, right? Power laws are like this, right? They're the El Dorado for of sorts. Have I got the right word? No. What's the mythical city? Is that right? Yeah. Yeah. For all sorts of people, but linguists here, physicists, all sorts of people. Like, I found the secret to the universe. This is yeah, like a John Cage film. Okay. No, what's his name? No, what's the guy? He's in all the terrible films. Oh, my God, I can't. Nicolas Cage. John Cage plays no music. Nicolas Cage. Yeah. Right. There's something. Well, he oscillates between good films and bad films. All right. So this was Zipf's story, let me tell you. I might as well put it out here. You can see there isn't, in the end, a math thing, but it's a reasonable general story. So he called it unification and diversification. So language is about communication, right? So you're transmitting information. And so you can see all this sort of information theoretic stuff coming out and all that kind of work. But it's easy for the speaker, in some sense, if they just have to say one word. That's going to be easy for the apparatus. You just have to say ook, 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 ook. Right? But that's going to be hard for the receiver. So this is his analogy. It's one tool for it. So you've got a hammer, and that's all you use, right? You use everything. You've got a teaspoon, and you do everything with your teaspoon, right? So you can get away with it. It's not great, but you can get away with it. Obviously, in language, disaster. So for the decoding side, it's great if everything points to one thing specifically, right? That would be very helpful. Of course, we've ended up, as you all know, right, with language words have multiple meanings, and actually English is extremely interesting in the way that over the last 1,000 years, a lot of extra material has been jettisoned, right? All this sort of stuff that was in conjugation of verbs that would tell you that this verb is actually relating to a pig that jumped over a fence. Like, from the word just being said by itself that those things are in the sentence. One of them will be over here. But we figured out that we can throw a lot of that away. And it means when we hear words in isolation, it's a little hard. So you have a specialized tool for every task. So encoding is simple, decoding is hard. Decoding is simple, but encoding is hard because you have to map everything out. And so he says there's a tension between these two things, and you end up with a "the," and you end up with haberdashery, right? You end up with words that are used a lot that help hold things together. They're common tools. It's not a bad analogy. I mean, it's true of a set of tools themselves, right? There are some things you use over and over, and then some that are very specialized. So at least, so that suggests an uneven distribution. Why it would exactly be this very kind of clean power law is, that's another thing altogether. Anyway, so that's kind of his argument. And then he says, I know everything. Okay. So I'll show you some more. This one I actually tried to do myself, and it's sort of there. So the number of meanings of a word, which gets at this, this problem, exactly, these tools can be used in different ways, increases its frequency to a half, at least over some range, at least for his, for a particular dictionary that he looked through, or he forced students to look through, as I will come back to. So this is number of meanings. So, right, so the more common a word, it's rolling over, the more common a word, the more actual meanings it has. So when you get right out to the very rare ones, they're very specialized. They really mean something. Article length in this thing that used to exist called the Encyclopedia Britannica. Not sure about the slope, but there's definitely, here's orders of magnitude, right? There's 1, 2, 3, 4, it's pretty good. This is population size of districts, so this is the city size kind of thing. There's only a couple of orders of magnitude, but it seems to be fitting a line. The exponent here is, it's alpha equals 1 is the claim. This is 2/3. I mean, now we're getting some funny numbers, right? So he's going for, this is a Pythagorean ideal, right? So we go for some nice fractions. We're not going to put in 5/12 or something. But it fits reasonably well. So this is the number of employees in organizations. What's this one? So news items is a function of the distance away from Chicago. And so that's Washington. So that's why it pops off. But this is using this quantity that I wrote up here before, well, some version of it. So population of Chicago times the population of the other city divided by the distance it is away, just as the crow flies. And plotting that as the number of news items. Right, so as this quantity goes up, you get more news items. So the way for it to go up is the population increases, or the distance decreases. So that's the so-called gravity law. There are, as I said, many more versions of that now and revisions and so on. Obituaries in the New York Times is a function of location away. I think this is Newark, New Jersey, so that was different. Movement of stuff, again, this kind of, right, so it's hard to see, but again, this is this gravity law down here, population 1 times population 2 divided by the distance between them. That's freight, it's actually railway freight. This is length of trip versus frequency of trip. It's unbelievable, so this is the number of trips here, this is the length of them, so the more trips you take, the less distance, it makes sense, but it has this particular decay. Here's the last one I was going to show you. So this is the probability of marriage. So this is distance apart of two people in Philadelphia in terms of blocks where they grew up. And it's only an order of magnitude here. So we're out to, 30 blocks apart. So your probability of getting married was going down. With this, he didn't draw a line through this one, but there you go. This appeared, so Steve Strogatz, we'll talk about him a little bit. He's Uncle Steve. He's a bit of a hero here. I'm just quickly show you this. This is the only thing that I've ever really seen about Zipf, the person. So Strogatz has this piece, you can go and read it. It's about Zipf's law that was in the New York Times a few years ago. He's a professor at Cornell. And then in the middle of the comments, there's this one from a fellow who was one of his students. And it doesn't suggest a good thing, I have to say. So he missed turning an assignment. There was an accidental death of his father. I mean, this is a terrible thing. And it comes back from the funeral, and Zipf said, just do the assignment, right? So he and his family sat around going through trade magazines and so on, getting out these numbers that appear in all of these graphs. So this is old school professorshipping. It's not great. Anyway, he gives him some forgiveness at the end, but that's all I know. So I guess he was kind of a crazy guy. Anyway, yeah, he died a year after that book appeared. He was only 50 years old. Okay, so this is one other piece I'll show you that's, as I said, lots of other things have happened. We had Marta come up from MIT a few years ago. She gave a talk. You can link to it here at TEDx conference. So this is about human mobility, right? So it's from cell phone data, and it's a very large data set. No one quite knows where it's from. It's a this is a bit of a weird thing. You know, usually you want to be able to tell people that, but it's one of these. It's for a European country who simply gave them the data. Said, we love your work, here are some data. But you're not allowed to say who it is. So this is looking at different kinds of people. They visit different locations from, you know, as they move around in their life. And so there are some that only go to a few locations, some that go to many. But this is the probability of being at a certain location. So you could imagine this is home and work, and then other places here, right? So there might be sports or a religious location. You know, so these are different places they might go to, and from which they communicate. So again, one of these zip floor type things associated with people in some way. All right, so there are lots of others. There's a whole like extra bunch of things here for you to look at if you want to, but that's good. All right, we'll go through these things. Okay, good. So 1949, it's a long time ago, and we're absolutely still sorting a lot of that out. Good. All right, so this is the opening of two pieces on power law size distribution, trying to show how we can get to them, right? So the first part is about random mechanisms, and well, so that'll be the first part, random walks. Do I have it in here? Yeah. So random walks, what the so-called first return problem. It's a very famous statistical problem, lots of interesting things, and it does connect in all sorts of ways to all sorts of other areas of mathematics. But this is a pretty clean, you know, we'll have to do some counting, but it's a very clean and kind of unusual thing. So I want to show you that first. It connects deeply, of course, to the normal distribution and the Gaussian, so that's all good. A lot of universality here. There's a piece in here of variable transformation. So we have some variable that's got some distribution that's fine, exponential, Gaussian, it's very reasonable. But it has some transformation to another variable that the transformation itself is the thing that leads the other variable to have a power law size distribution. So we'll see that. We'll have some fun here. But this will come back to help us when we look at robustness of systems. What kinds of systems explode? The emblematic one is so robust yet fragile, right? No, right. So they look good most of the time, but then they explode. Okay, so we're going to visit this place, the Snormals, the Gaussian distributions. But it turns out, so these are pretty boring things, but inside them, there is actually an aspect in here where we get some element of random walks, which are connected with these things that give us these weird size distributions. And then somehow these guys are hiding inside there. All right. We will really get to those in the second section of this, which is much more about dynamic growing mechanisms. Because that's ultimately what you want. All right, so randomness. Randomness is awesome. It's great. It's everywhere. It's happening all the time. It can be a problem, but it can help create and grow things. And it's always testing, you know, systems. And it's a fundamental aspect of nature. Things are popping in and out of existence because it's this mad quantum behavior. We have that sort of thing. And we have that kind of fundamental randomness, that, as far as we can tell. And then you have the whole dynamical systems, chaos business, right? So that even deterministic systems functionally behave randomly in some, can functionally behave in random ways. So random walks. Let's talk about these. It's very simple, and they will appear in lots of other places. Okay, so one spatial dimension, and we're going to just take time and space to be discrete. So it'll be a counting problem. Data science is full of counting, so it's good to be good at counting. So let's say we have someone who's not doing too well. They've drunk too much, and they start at some origin x equals 0. So you can think of this as right, you just have here's x, here's 0, 1, 2, minus 1, minus 2. So this seems pretty innocuous. They're just going to randomly walk away, flip a coin, and then they could come back, they could randomly walk. And so I'll have some plots in the next thing. Let me So we'll have x this way, and we can make time go like that, so we can think, oh, so they're going to wander like this. Right? So I asked you some of these probability things the other day. So I sort of a little test that people in statistics like to do is, have you done this, where you write down 100 zeros and ones randomly. So you have to produce, you just have to write down 100 zeros and ones. And so the game is often, so you take half the class and you say you can do it at home, or you have to do it here. And then it's easy actually, so you get people to bring up their things and you say, you cheated. So, because you get people to actually flip a coin, right? So that's the request. You have to flip a coin. Heads, tails, heads. So actually flip a coin. That's annoying, 100 of those. So of course people will start to just, But there are patterns in a random, in a random sequence of 100 things like that we don't produce very well, because we'll go head, but then we don't want to put in long runs, but there will be. I think there's a 50-50 chance you'll have a run of 7 heads or 7 tails somewhere in there, which looks a bit strange to us, right? Our brain will try and tell a little story for why that is. So it's actually easy to spot when someone's cheating, when they're trying to be random. It's hard for us to be random. Okay. All right, so we're going to have this little epsilon t. It's going to be the step that you take at time t. So with probably a half, you step to the right, and probably a half you step this way. And you can have biased random walks. You can do all sorts of things. You can say, there are lots of examples where you say, okay, you start off with some money, and this is when you run out of money. When you're gambling, right? And you talk about ruin type mechanisms, and what's the chance you will get to the ruin place? It's always 1. Disappointing. So here are just a few realizations, right? So we've got 10,000 coin flips, which would be very hard to do, and these are just little random walks, and they have a little bit of these can be odd things for us to look at. I mean, yes, there's obviously some randomness, but you could start to tell a story, right? And I have a thing much later on in the course, which is a XKCD cartoon, which is exactly this, I suppose. The stock market is up, the stock market is down. Let's tell a story, right? Sports works like this as well. Like you can explain, you can add a narrative on top. We do that very, very easily. And it turns out you were looking at upside down, and then you add the opposite narrative very quickly, right? The screen was upside down. Like, oh, the opposite was happening. Well, that's because, so you see it all the time. All right. So the thing we're interested in here, is, so it starts at 0. What's the chance that it comes back to 0 at a certain time? Our fellow who's lurching around, or human, is lurching around. What's the probability that they get back at time t? Well, given a time t, what's the probability that they come back? And then we might say, well, given that they started here, what's the probability that they will come back, they will have returned by time t equals infinity? I mean, obviously they should come back, right? Sure. What's the average time it will take? What's the variance of that? Seems like a pretty innocuous thing. I mean, they should be, you can see this one, right? They're back. Although, this one is sort of taken off a little bit. All right. Let's look at some very basic elements here. So we have these little epsilons, so that's a +1 or -1. So after time t, we simply add up all these little realizations. Okay, that's where we are. So our average displacement, we take an average of this guy, average of the sum, so sum of the averages. They're all independent. It's nothing bad. The average displacement for each one is 0, right? Half a chance you go that way, half a chance to go that way. On average, you don't go anywhere. But of course you do. So that's 0. Sum of zeros. All right, fine. So on average, right, we expect, so at any time, you actually expect your drunkard to be back at home, right? Back at the pub. Now, obviously that's wrong when you have even-numbered steps. Odd-numbered steps. So it's just wrong already. Okay, so we know that. Yeah. All right, so it's a funny business. Okay, so let's look at the next statistical piece, which is the variance. So the variance of x of t is, again, it's the variance of the sum, and that's the sum of variances, nice property of variances. The variance of one of these little beasts is right, so the variance of a quantity, well, let's just say x. That would be bad if I do that. Variance of some quantity x is equal to the mean of x squared minus, right, you can figure this out. I mean, this is the same as saying it's the x minus its average, all squared, the average of that thing. Right. These guys are the same. So we can take what this is the second moment minus its average. And we know this is already 0 in this case. So the variance of one of them, let's do an epsilon. We'll just take an epsilon. It's the average of the second moment minus, I was going to use that thing. I didn't use the thing. Epsilon squared. So the average of this guy is equal to 0, so this is gone. And this one, well, what's the average of epsilon squared? It's a half times minus 1 squared plus a half times 1 squared. Right? That's probably that you go left or you go to the minus 1. That's the actual value squared, this guy. So this is a half times 1 plus a half times 1. So it's 1. So the variance of one of them is 1. So the standard deviation is 1. It's the square root of it. So we can add these guys up. So we're adding these ones up, and we get t. Right? They're all 1. So we're going to add them up. So the variance for our random walk at time t is actually t. So that's some width. So therefore, the standard deviation, which is really the characteristic kind of width, is the square root of that, is t to the half. Right? This is a classic signature of random walks, and also how Gaussians grow. But this is a nice little scaling law. We'll get to scaling laws much later in the class, in the course. But this is it's not trivial. I mean, it's got a nice little story to it, but it's not trivial. And we could call this additive aggregation. Right? We're just adding things. It's memoryless, except for the fact you know where you were in the last time step. Right? You don't remember anything past that, and you don't remember if you had a +1 or a -1 beforehand, right? So that's all gone. Okay? So Markovian. So that's a nice little interesting non-trivial scaling law. Okay, I was going to show you this. I might do the Radio Lab thing where you talk over the top of it. Let me see. Maybe I'll do that. So this is just bean machine, the Quincunx, Golden box, the various things. There, you can see up here, it's this bit. There are all these little balls falling through. So there's a little guy bringing this stuff up. They're dropping balls through it. And it's going to start forming a normal distribution. Now we need to come back here. Can you see this okay? So what they're showing in the background is actually a histogram of, I can't remember what it was, the guy actually says returns or something like that from the stock market. So it's actually something from, so you can see there are these little extremes out here. And the claim is that this is fitting a normal distribution, although I'd be worried about those pieces. So this is one of these situations where if you take a log, it starts to open it up, right? You need to see that that's a minus x squared, e to the minus x squared decay. And it can be a little, yeah. Anyway, so the balls are falling down. So we're getting random walks here because they're starting at the top, they hit the first one, and then the first little rod, and then they bounce left or right, and then they hit another rod, left or right. It has to be set up quite precisely. So you're actually creating all these little random walks. And this is a problem that you'll solve in your in the assignment. So a bunch of random walks, where they end up at time t, right? So on average, you expect them to be in the middle. You expect it to have a standard deviation of square root of t. And the shape that you start to see is a Gaussian, right? It exactly gives you the Gaussian. Okay. And you can, binomial probability, you can think of this in different ways, but and compute it in different ways. But this is it should be starting to fill up. It's terrible. I don't know why, they filmed it with the light behind it. It's hopeless. Yeah, anyway. I'll mention this later on, but there is a really weird history in economics of thing that happened in the 50s when a guy called, what was his name? Bill Phillips in England invented this contraption, which is it's a fluid thing. It's full of fluid and pumps and dials and all sorts of things, and it models the British economy. And it was used up until the 80s because it could solve pretty good complicated partial differential equations. And nonlinear things, no problem, right? So it could do it. And it's still used, I think, as to demonstrate things, because you can be the person who changes the interest rate over here and so on. But it's fluids. It's a very, it's called the Moniac. It's a famous odd thing. Okay, this one's good. That's hard to do, yeah.
He gets that one over. That has never happened before, incidentally. That was an historic moment on The Price is Right.
Every moment is a historic moment on The Price is Right. But like, so it's interesting to think about this because they're actually, you should know this is a Gaussian story. Oh, hello. And I guess you get 0 here, right? Big fans, perhaps. This one looks like on average, this is where you end up, right? But it's going to be hard. Anyway, so they had this. These structures have been around for a long time, and there are little games you can get. The Romans had them. I mean, it's an old thing. All right. Okay. So let's figure out how to do this, or how to mess around with this thing. Yeah. Okay. So each random walk, so you've got all these random walks. You can think of the ones that all end up at the same point, but each one has its own little history, right? So there's a differentiation between the ones that end up at the same point, and we sort of say that's the same. But they all have their own little history, and each one's history, each walk occurs with probability 1 over 2 to the t, right? There's a half a chance of it this way, half. So there's that. So there's a specific shape that could matter. But in general, we're more interested in how many end up in the same place. Right? So we'll do that. We'll say, let's say we start at x equals I, and there's some lurch around for t time steps, and then we want to know how many of those walks are going to end up at j. Right, out of all the possible walks. Now it's a bit, the framing here is that you can think of all the possible walks. There are 2 to the t possible walks. Right? After t time steps, you've made 2 to the power of t. So you've got this exponential increase in the space of walks. All right, so how many of them end up, if I start at position I, they end up at j. So the basic thing we need is that it doesn't really matter where you start, you just need to move by this distance, j minus I. Doesn't matter what these numbers are, j minus I is the displacement you have to end up with. So the one we're kind of interested in is 0, because I was talking about coming back, but we'll get to that. We'll have to get to that after t time steps. Okay, so that's a problem for you to work out. It turns out it's a counting problem, and we end up with this simple binomial. Well, it's a binomial. It's t, the number of time steps, and at the top, and then t plus j minus I, so that's the displacement divided by 2. So you have to figure out how you get that. And if it's so it's impossible to do certain kinds of walks, right? So you certainly can't get outside of this cone of possible steps, right? So if you have to take +1, +1, +1, +1, +1 to get there, that's the limit, or -1, -1, right? That's the limit. Anything outside of that cone is impossible. And there's also the problems with even and odd, right? So if it's an even displacement, you can't get there with an odd number of steps. Anyway, so we can kind of ignore that little bit and dance around that. All right, so that's a problem to work out. So let's get this to work as well. So this is good. So we're going to bypass this even odd problem by saying, all right, well, let's have an even number of time steps. Okay, 2n. So t is just 2n. So after 2n time steps, we could be at 0, ±2, ±4, like I was saying, plus or minus 2n. Fair enough? Yeah, it's exciting. It's got to be even. We've taken an even number of steps. So we'll just say it's 2k, right? Some value. So we have this expression, which you figure out in the assignment. And so it was nijt. Let's go back to it. This guy, right? So we're going to have a 2n here, a 2n here, and we want this guy to be a 2k. Is that right? Yeah, okay. So, yeah. So we're starting at I equals 0. We're ending up at 2k, whatever that is, and we've had that many time steps. So this was the t on top, 2n, and then we had t plus I plus minus j divided by 2. So we get 2n plus 2k, and then divided by 2, we get n plus k on the bottom. So it's a probability. I've turned it into a probability now. We'll get the normalization sorted out later on. But this is a binomial, so right, all these things are connected to each other. So this is a binomial, so you have to figure out how this thing behaves for large n and large k. So it's factorials, right? So what do you do when you've got a factorial in front of you with a large thing in it that's growing? N factorial. How do you represent it? How do you write down its asymptotic behavior? What is the... You have things in your pocket, right? So there's L'Hopital's rule, for example. That's a good one to have. You know, it's on the side of your little Swiss Army knife. A few other things floating around. This is a good one to have. You use this a lot. Stirling's approximation? Nope. Okay. Yeah? All right. So Stirling's approximation. So it is a Stirling approximation, but it's Stirling, of course, in math, people name it after humans. Which is a bit silly, right? Lobsters would name it after lobster names. Anyway, it doesn't really help us, but it's STIR. Okay, Stirling's approximation, really cool thing, but you'll be able to use that, and that translates into here, which is kind of crazy, right? So this is, you can go from here to here. There are other ways to get to the Gaussian, but this is our Gaussian, the very famous Gaussian distribution, right? E to the minus x squared divided by 2t. So that's exactly where the standard deviation is in here. This is normally, you might write sigma here or sigma squared there. It's a root t. Sigma is root t. Right? That was what we put down. Pi likes to be everywhere, so pi appears here. Pi is a good guy. That's also a good problem to figure out. Okay, so the things that you're going to, little tricks and so on. So Stirling's approximation is for factorials. What's the superfactorial? Who knows what a superfactorial is? So factorial is about the integers, right? If we step outside of the integers and we want to still have a factorial kind of story going on, what is the thing we are now? Yeah, so the factorial is a function of the integers. Yeah. So let's say I go over to a half. What's a half? Yeah. Well, you can go to, complex numbers, why not? Because we're insane. I don't recommend it, but real numbers, why not? What's a half factorial? Yeah, right, okay, so that's gamma. Gamma functions is the thing, yeah. Did I say that? It's minus a half factorial, I guess. I'll get it right, but there's a shift of 1. Yeah, so it's the gamma function. The factorial becomes the gamma function. When we move out, right? And the gamma function shrinks back to being the factorial. Yeah. So it's root pi, which is very silly, right? It's a half times minus a half times minus, sort of, but not really. It's not true. Okay. All right. So you're going to use those things. They'll appear in a number of places. They're very good, lovely little beasts, and they will help you here. Okay. Right, so we had random walks, and somehow we end up with this beautiful, fantastic story, right? The Gaussian. I mean, that's a universal object if we've ever had one. I've put a link here to stable distributions, which you, if you get really excited, you might go and look at those. So Gaussians have this, I mean, among many properties. One is if you add two Gaussian variables together, the resultant, so x is distributed normally, y is distributed normally, then their sum is distributed normally. And so there's a family of distributions that are like that, and they're called the stable distributions. And all of them, as you move away from the Gaussian, have power law tails, actually. So there's this whole, a little bit of a bizarro world of so-called stable distributions, which are, so, you know, have this kind of, they have a sympathy to the Gaussian. All right, yeah. The inverse Gaussian is in there. There's the Laplacian distribution. There are lots of other funny things. All right. Okay, that's cool. Cool. Yeah, so this is kind of what's going on, right? So here's one little random walk, ends up here. But we have a whole bunch coming out. Some very rarely will get up to here. So 2 root t is the, there you go, your 95% confidence interval. Most of them will be in here. You'll get, very rarely you'll get one that's just all the way up here, but that's extremely unlikely, right? It's 1 divided by 2 to the power of t. And what's happening is you're getting, if you look at where they all end up here, that you get a Gaussian, you get a Gaussian, you get a Gaussian, and that Gaussian is spreading apart, right? So its variance is growing as t, its standard deviation is growing as root t. So if you looked at that contraption where things are falling down, or the Plinko thing is falling down, you know, the further you put the containers down, the more little rods you have for bouncing around, the wider it spreads out, and it grows like root t. So I'm going to call it this. No one else calls this, but I'm going to call it this. Random additive growth, right? So it's randomness, it's additive, and it's growing. So we'll get to other kinds of mechanisms. But this is very simple. So it's diffusion, right? It's a very incredibly important central part of kind of the physical world. You know, it's the whole entropy is growing. We're going to be a big soup one day, which seems sad. Complexification seems to be going against that, but so anyway. Second law of thermodynamics, right? We can't argue against physicists because they must be right. Sure, black holes exist. Sure, knock yourself out. Okay, so we visited the Snormals, and this is how we got there, right? So there's a little more in here that you'll understand, right? I guess, so here's our random walk, sort of a Charlie Brown thing. And there's our t to the half. That's a little piece there. Exciting. All right. Okay, so that's good. That's normal. It's the Snormals. Good stuff. Had some scaling in there. Let's do this. Start off on this first return business, which we'll get a fair way through. We should get through. Yeah, we should. Oh no, there's all this other stuff. All right, so yeah, this will be on Thursday as well, of course. All right, so let's write down this new thing, C, RT. So probably that by time step t, a random walk has crossed the origin r times, been back r times. Right, so we have I had those examples with 10,000 iterations, so we have a coin flip game. So kind of things you might want to know, you're playing against someone and they're taking your money. If you're behind early on, what's the chance that you come back, right? The most likely number of lead changes is strangely, it's 0. So the most, right? So if you're at time t, the most, this is a bit deceptive, right? So, but the probability that you've had 0, it's come back 0 times after time t, independent of t, right? This is t, just t, is greater than the probability it's come back once. It's greater than the probability it's come back 2 times. You can sum all of these up, and that'll be bigger than this guy. But that's a probability that you've come back at least once. But this is a bit odd. You might think it's kind of peaked in the middle because you know straight away you go out, you have half a chance of coming straight back, straight away, right? So half of all walks immediately come back, right? You go this way or this way, and then half of them come straight back, and the other half go that way. And they're not that far away, so you'd think you'd come back. Okay. Pretty weird. Okay, so here's the weirdest thing, is the expected time between tied scores, or the expected time for this drunkard to come back, the average time that it'll take for them to come back is infinity. That's really, really weird, right? Because you know in 2 time steps, half of you send all your drunkards off, right? They're all leaving. Am I allowed to use this analogy? But it's kind of a classic one. They're all leaving, and 50% of them will be back straight away, right? But on average, so you say, all right, well, they took 2 time steps. So 50%, you put a 2 next to them. 50% get a 2. But then it starts to decay in such a way that the average number of time steps is infinity. So that's really strange. All right, so we're going to try and figure this out and see what's going on with that. So if you really like probability theory, you can get into Feller, volumes 1 and volumes 2. Awesome. All right, so it's the first return problem, this is known as. So it's quite beautiful, and we'll get ourselves a parallel size frequency distribution out of it. All right, we're starting with randomness. Let's start with randomness, it's good. So, so we're in 1 dimension, one spatial dimension. We've got t time steps, right? These basic questions. So this is also a bit unsettling, right? So I'm claiming we have to figure this out, that on the probability the average time they'll take is infinity. I mean, some of them might escape, right? Fair enough. And then you can say, well, what about higher dimensions? So let's put it on a 2D grid and then let them walk away. There's a famous old problem actually in mathematics, and it goes back into the 20s, and Polya thought about this. What about 3, 4, 5? So there are more ways to escape in higher dimensions. So you think it should, things should get worse, right? Because you're in 20 dimensions, you walk away 1 step, now you've got, I'm going to say the wrong thing. You've got 20 dimensions, so you've got 39 directions to go in that aren't back home. Right? So as soon as you go into 2 dimensions, you go up 1 step, you've got 3 places to go, which isn't the origin. Right? So now you've got a quarter of a chance of getting back. Okay. Good. Reasons for caring. You love this. All right. So we get an interesting story out of this. It's very surprising. So that's why we're doing it. And in general, randomness is just around, and some physical structures actually could have random walk barriers, and we'll talk about that. That will give me an opportunity to tell you about scaling laws, scaling relations. And that's what this is. We'll see how different scalings relate to each other. We already had this small one with the Zipf's law and the very fundamental kind of one, Zipf's law and the size frequency distribution. But you can have different exponents connecting to each other with part of a system. So for example, one we'll come to much later on, you might find that the way heart rate scales as a function of size of mammals, the way the exponent involved with that might be connected to an exponent involved with their lungs, exponent involved with their dimensions in some way, how much energy they use, right? We'll get to that later on. How big the aorta is, there's all sorts of claims about that. And what you want to do is say, all right, well, there's actually really only 2 exponents that matter. All the others follow from that one. So if you can do that, that's an important part of the description. All right, so here's our random walk. This is a bit of a tricky problem. Let's set up and see if we can figure out how to do this. Okay, so here's just one example. We're going to have an even number of steps, and so this is after 20 time steps. We'd like to see, how many walks actually end up here for the first time after 20, right? And then, of course, 2n time steps. So, of course, a return can only happen when we have an even number. So it happens here at 8 and 10, and then again at 14. So we'll write it like this. Probably a first return 2n. So probably that the walk first returns at time t equals 2n. And so probability and counting, right? So combinatorics and probability are deeply connected with each other. So we'll sort of flip between those 2 things. I like counting, so we'll go for counting a little bit. Combinatorics, statistical mechanics and physics, combinatorics and math, they're all very connected. So we're going to make this return problem simpler by turning it into an easier kind of return problem. So it's going to be easier for us to say, that it's simply returned. Not for the first time, but it just simply has returned. We can compute, that's actually easy to compute because we had that formula before, right? The NIJT. We can say NIIT. So what's the probability that you start at I, you end at I after time t? We've actually got that already, regardless of how many times we've crossed I. So we've already got that. So let's simplify things a little bit. Let's assume they've gone this way to start with. So there's a symmetry issue. So we're going to go this way. So here's an example of exactly what we want, that they come back at in this case, our time is 16. So just an example. So we have to have, pretty clearly, we have to have that the walk can't come back in any intermediate time. It has to be at 1 here. And then, of course, there's a walk that goes this way as well. But we want the one that goes this way. So it has to be here. It has to be here. It can hit 1 at any point in between, as long as it's even. It can or odd. It can hit. So that's fine. So we can have ones that bounce like this. Right? So that's going to be a slightly easier thing to get at. You know, in the way with most mathematical kind of explanations, we travel through some kind of path, and it's not really explained that how many monks died to get there, right? So I like to think of monk lifespans as a measure for how hard something is. But, you know, it's like sort of theorem proof, you know, and there's some mention about you shouldn't touch that plant on the way through, or don't put your foot in that thing. They just like casually mention it, but it turns out that, you know, it's full of dead bodies. Or someone spent their whole, you know, life working on that piece, and it turns out it's a brick wall. So yes, we are navigating in a particular way, but this is a horrible way we do some things. But no, I'll try as much as possible to show bad ways to do things. But this is a little bit of like, oh, look what we solved. Here's the sneaky, you know, trick. Okay. All right. So this is okay. We can have walks that return but don't cross, but return and don't cross. So let's see if we can get those. So they're allowed to come back. So we could chop this part off and say, okay, we'll take all the walks here. Every walk, if we can count all the walks that return that don't cross but return as many times as they want to be in between, that's okay. So that's what we'll do. All right, so this is a statement of it. So probably the first return at 2n. Ignore these for a second. So it's probably that our walk is at least 1 for all of these time steps in between 1 and 2n minus 1, and that it is actually 1 at these endpoints. And then we have to count a few things. So a half is here because this walk, there's another walk that goes this way, so we only want half of them. And then we get 2 for the flipping, because we've already gone one way. So that's what these things say. Okay, the lurching went one way. All right, so that's a bit of trickery. All right, so a bit of trickery already, and then we have to do another tricky thing to solve this. Okay. So we're going to count walks. We'll get probability at the end. So this is a piece that you guys will figure out. So again, it's the number of possible paths or walks between I and j, given that you take t time steps. Okay, so now we're at x equals 1, and we want to end at x equals 1, and we want 2n minus 2 time steps. So we can put those things in there. That's almost what we want to do. But this will count walks that go underneath it as well. That's a little bad. Okay. So here's the idea. So here's the idea. So we're going to count, we want all of these walks that just hit here and end here, and then I'll step down like that. That's fine. So what we want to do is find, but our calculation, this n 1, 1, 2, n minus 2, also counts these walks. So it would count a walk that went like this. It would count that walk as well. And I'll show some more pictures, but it would count that walk. So if we can find all the walks, this is all of the walks that hit 0, that actually go off and subtract them off, then we'll be set. So we know the total number of walks that go from here to here. If we can find the ones that do the wrong thing by hitting 0 at least once, we can subtract them off. That's the idea. So I'll show you some pictures. We'll call them excluded walks. And we'll use what's called a method of images. So this is used in lots of different calculations, but this is a sneaky, sneaky trick. All right, so here's our sneaky trick. Okay, so this is a bad walk. Starts at 1, ends at 1, but it hits 0. So we don't want to count that one. So one way of identifying is mapping it 1 to 1 with a walk that starts at -1 and ends at 1. So this is a mirror flip here, and you flip it up until the first point of crossing. So this blue one looks exactly like that walk if you flip it here. So what's happened? So here's another example. This is a bad one. It actually went beyond 0 into the negatives. So we'll do the same thing. We'll say, okay, this blue one matches it, and we have a 1-to-1 correspondence if we flip the first part of it up. So the claim is that we can count all of these walks from -1 to 1. And so you can take any walk from -1 to 1. So here's an example. You flip it up like this, the first part, until it, the first part of the walk, because it has to hit 0 at some point, and then say, okay, this is a bad walk. So that's one of the excluded walks. So what I'm saying is we can count all of the bad walks in this way. Ugh, let me say it properly. All right, so for every walk that starts at x equals 1, ends at x equals 1, all these ones we want, every one that does a bad thing, there's a unique matching one that starts at -1 and ends at 1. Right, so it matches the path until it hits the origin, until it hits 0, and then it's a mirror of it, and then it just matches it afterwards. Okay. Yep. So then the number of paths that start at 1, end at 1, and do not hit 0 is equal to the number of total paths between there minus the number of paths that start at -1 and end at 1. Hour and 15 minutes. It's possibly hurting. Okay, so let's come back to this one on Thursday. We'll explain it. I'll just show you you'll do this. Well, I'll recap this a little bit, but this is for assignment 2. You're going to show that this result holds, which is pretty cool. So it's going to be end of the 3 halves on the bottom. So we'll talk about that on Thursday, and then we'll go into some of this other madness. Okay. All right, liberation. Random walks, extremely, extremely interesting, important things. Thank you, people.